Hello friend, today we will discuss the topic crystal field theory. I am Dr. P.R. Mahalle, Assistant Professor and Head, Department of Chemistry from Led Bhaskar Singh Arts, Professor Narayana Gonda Science and Ashalata Gonda Commerce College, Sakalpilla. We will see first the introduction. The crystal field theory is an electrostatic model which considers the metal ligand bond to be ionic arising purely from the electrostatic interaction between the metal ion and the ligand. The essence of the theory is that the 5d orbitals which are degenerate, that is equal in energy, the free gaseous ion of the metal ion become differentiated into a level of different energy under the influence of electrostatic field of ligands. We will see the postulate of the crystal field theory. This theory considers the complex combination of the central metal ions surrounded by different types of ions molecules with electrical dipoles. These are called as ligands, and these are regarded as the point charges or the point dipoles. The bonding between the metal cations and ligands arises due to the attraction between the nucleus of the metal ion and the partial negative charge present on the ligand. Thus, the bond between them is purely ionic. The interaction between the electrons of the cation, those of the ligands, are entirely repulsive, and these repulsive forces are responsible for the splitting of the d orbitals of the metal cation. And therefore, we can say that in the simplest form, the crystal field theory does not consider any overlapping between the metal orbitals and the ligands. The d orbitals, which are degenerate of equal energy in the free metal ion, have their degeneracy destroyed by the approach of the ligand during the formation of the complex. We can see here the metal ion surrounded by different types of ligands on the free coordinate axis. Now we will see the different types of d orbitals. The shape of the d orbitals. First, the dxy, the dyz, the dzx orbital, and the dx square minus y square and dz square orbital. Now we will see the d orbitals which are degenerate. We will see the crystal field splitting of the orbitals in the octahedral complexes. The d orbitals which are degenerate of equal energy, free metal ion have their degeneracy destroyed by the approach of the ligand during the formation of the complexes. In octahedral complexes, the dx square minus y square and dz square orbitals, which point towards the axis along the direction of the ligand, will experience more and will be raised in energy, and dxy, dyz and zx orbitals, which are directed between the axis, will be lowered in energy relative to the average energy. Thus, 5d orbitals will be split up into two sets: T2g orbitals of dxy, dyz and dz of lower energy, and Eg orbital dx square minus y square and dz square of higher energy. The energy difference between these two sets of orbitals, T2g and Eg, is called as crystal field splitting energy, and it is represented by delta O, where O is octahedral field. In octahedral complexes, the energy of the two Eg orbitals will be increased by 6 dq, and while that of 3 T2g orbital will decrease by 4 dq. And therefore, the average energy, that is barycenter of the d orbital, should be same, and due to center of the gravity rule, the algebraic sum of all energy in orbitals should be 0. The additional energy which is responsible for stabilization of the complex is called as crystal field stabilization. Crystal field splitting of d orbitals in octahedral complexes can be shown as in the following diagram. The relative energy where the d orbitals in the free ion, then on the approach of the ligands, they are split into two types of orbitals, Eg and T2g orbitals. Now we will see the crystal field splitting of d orbitals in the crystal field splitting in the tetrahedral complexes. The dx square minus y square and dz square orbitals, which point towards the axis along with direction, will experience less repulsion, and therefore they will be lowered in energy, while the dxy, dyz and dzx orbitals, which are directed between the axis, will be raised in higher energy relative to the average energy. They are repelled by the ligands, and therefore the 5d orbitals will again split up into two sets, T2g orbitals of higher energy and Eg orbitals of lower energy. The energy difference between T2g orbital and Eg orbital is denoted by delta T, where T is for tetrahedral field, and it is being found that delta T is less than delta O, which is due to the less number of ligands in the tetrahedral field. The tetrahedral field, the energy of the two Eg orbitals will be lowered by 0.6 delta T, and that of 3 T2g orbitals will be higher than 0.4 delta T. Again, the average energy, that is barycenter of the d orbital, should be same, and due to the center of gravity rule, the sum of the energy will remain 0. Here we can see the crystal field splitting of the orbitals in the tetrahedral complexes. Now, crystal field splitting of d orbitals in square plane complexes. Due to the removal of the axial ligands, the energy of the dz square decreases while that of dxy increases. So the sequence of the energy becomes dxy is equal to dyz less than dz square less than dxy less than dx square minus y square. Here we can see the splitting of the d orbitals in square planar complexes, which is deviated from tetrahedral complexes due to the change in the field strength of the dxy and dz square ligands. Now we will see the factors of crystal field splitting in octahedral complexes. While considering the nature of the metal ion, different charges on the same cation of same metal ion results in the higher charge on the central metal ion. Higher is the crystal field splitting, and therefore this is due to the fact that the charge on the metal ion increases, ligand will be drawn more closely to the electrostatic field will be greater and resulting in the larger splitting. Again, the same charges on the cation of the different metals is again the factor, as cation of different metals with same metal charge have different number of d electrons. Thus, for such complexes, crystal field splitting decreases with the increase in the d electrons. Again, in the factor, that is considering the nature of the transition series, the series from 3d to 4d to 5d series, the ionic size of metal increases. Thus, the magnitude of the crystal field increases, and this is due to the reason that the better overlap of the orbital with the ligand orbitals. The geometry of the complex is also one of the factors. In octahedral complexes, the splitting of the d orbitals has been found at more than twice than in the tetrahedral complexes of some metal ion and ligands. Nature of the ligands and spectrochemical series. Strong field ligands have greater splitting law, and weak field ligands have weaker field, less splitting ability, and therefore strong field ligand exert strong field strength while weak field ligand exert weak field strength. And as compared delta O, the strong field ligands have higher value as compared to weak field ligands. Now we will see the spectrochemical series. It is the series of the ligands in which the ligands are placed according to their field strength. Here we can see in the electrotechnical series the ligands from iodine to aqua, that is H2O, are called as the weak field ligands, as they exert the weak field strength on the central metal ion, and from thiocyanato-N to carbonyl ligand, they are termed as the strong field ligands, as their field strength is increasing. Now we will see the crystal field stabilization energy. As we have seen that additional energy which is required to stabilize the complex due to the crystal field splitting, it is denoted by delta O in octahedral field and delta T in tetrahedral field. For octahedral field, crystal field stabilization energy is given as follows. For tetrahedral field, it is given as follows, where the number of electrons in T2g and Eg orbitals, and the m is the number of electron pairs, while p is the pairing energy which is present in the crystal field stabilization energy. Now we will see the crystal field stabilization energy here. The weak field ligand and strong field ligand are placed in the region of configurations from D1 to D10. Now we will see the applications of crystal field stabilization energy. Crystal field stabilization energy is helpful to explain the deviation that occur in the heat of formation of the transition metal complexes. It is useful to predict whether the resultant complex will be high spin or low spin and stereochemical reference. CFAC has been helpful to explain the deviation that occurs in the lattice energy of the divalent, trivalent orbital halide. Now we will see the limitations of the crystal field theory. It gives the total emphasis on the ionic bonding and partial covalent bond, while the character of the metal ligand bond is not considered. CFT considers only metal ion D orbital without giving any consideration to the metal orbitals such as s, p orbital. It does not consider the ligand orbitals, and therefore their interaction with metal ion orbitals are not explained at all. Pi bonding in the complexes is not considered, and therefore it is the limitation of the crystal field theory as it presents prototropic complex formation. It fails to explain the relative strength of the ligand. This theory again fails to account the charge transfer spectra, and crystal field theory is not explained. Crystal field theory does not explain the Navier-Stokes effect properly. So this is all about crystal field theory. So I wish you gained some information about crystal field theory. Thank you.